All right, so here's the last thing. If R is semi-quasi-local. And remember, what this means is it's got finitely many maximal ideals. And I is invertible. Then I is principal. I left the semi-quasi-local. We proved this for quasi-local for just one maximal ideal. I left the left of it as an exercise. In this example here, I can't resist to point it out. This thing, this ideal I is invertible. It's an invertible ideal of this, but not principal. So this is a backwards way of showing this thing has infinitely many maximal ideals, right? So, and of course, that's fairly easy. As a matter of fact. Let me give you this last theorem before we talk more generally about proof domains. Let's let I be a finitely generated. Yes, we do. I'll say something fun. So here R is an integral domain. Let I be a finitely generated ideal, then I is invertible. If and only if I localized to M is principal. For all M in max spec R. Okay, so let me just in case, let me explain some of this terminology. How many of you have ever heard of the spectrum of R? Run across that assumption. It's a set of P and R, since the P. So the spectrum of R is just a collection of all prime. So we feel fancy about ourselves when we call it the spectrum. And now that I've told you that, this will probably make this a little bit easier of a pill to swallow. This is a set of M in R, such that M is max. So it's a set of ideals that are maximum, it's max spec R. And I guess I want to tell you what this is. Suppose I in R is an ideal and E is well, actually, let me do this. Yes. Okay, so suppose that I is some ideal in R and S is some multiple set. IS and RS is an ideal where this is exactly what I think you might think it is. So R over S are fractions where the denominator, or I'm sorry, the numerator comes out of R and the denominator comes out of S. I localized it as is the numerators now come out of I instead of all of R. So when I say I am, this is the set of alpha over S, where alpha is in I and S is not in, you know. Because it's ideal. Okay, so let's do the proof of this. Proof. Um, or so check this. So given I know how to form IS. I know how to form IS inverse in the same fashion that I form the inverse of any ideal. All right, check that if I inverse is R, then IS inverse is RS. This is fairly easy to verify. So if I is invertible, then IS as an element of RS is invertible as well. So in case that S is R minus some maximal ideal, IM in RM is invertible. Specializing in this case, but RM is quasi-local. Because this localization has only maximal ideal M. Therefore, IM is principal. Simply as we say, this property means that I is locally principal. It's principal of the localization of every maximal ideal. So this is one direction of proof. I is invertible, and as you may guess, it's the easier direction of proof. On the other hand, so let's do this here. Let's suppose that I localize M is principal for every M in the maximum on my spec. Now suppose I am principal for all M so you find out that this is, now there's going to be kind of an interesting twist here. By hypothesis, I is finitely generated. By the way, let me point out that we didn't need the finitely generated hypothesis in the first direction because the assumption I is invertible took care of that because one of the discovered is if you're invertible, you're finitely generated. On the other hand, let's throw in the I localized M on the surface of it. Doesn't seem like that's finitely generated. So let's let let's use our hypothesis. I is generated by this set. Assume that I inverse is contained in M. Let's assume that this is the case, right? Which of course, if this were the case, then if I is invertible, which is what we're trying to prove, if I is invertible, then I inverse is equal to R. If this is not the case, then it's gonna be stuck in some maximal ideal, because it's not a contained any maximal ideal, it must be all of R. Let's suppose that the generator of IM is Y. So it's generated by Y, it's an ideal of R localized at M. And so I'm gonna kind of think locally, act locally here. Note that for all Xi, we can find Si. For each Xi one of its generators, we can find Si in R minus M with the property that Si Xi is in the ideal generator of Y. So really what this is saying is a translation of this is, let's say, some RY over SSI. Like, so there's something in, and in fact, you could actually take SSI, you could actually assume that Y is in R, actually. And in fact, I don't know if I want to assume this yet, I've forgotten that detail for the moment, but you could actually assume that this Y, this generator by localized to M is actually in R if you wanted to, like just by stripping out the denominator. But anyway, so, and the reason this is the case is because, of course, this I is contained in I localized to M, so each of these Xi's must be a multiple of Y locally, right? So let's let S be the product of all these SIs. Product of all these here. And notice that SYI or SY inverse conducts each XI into R. So yeah, we will take this generator of local ring to actually be in R. We can do that. So notice that each SI conducts XI into Y. Actually, it's an element of as an ideal in R. And so the product of all the SIs conducts right. SY inverse conducts each XI into R. There we go. Right. Everybody, because each of these is some YR. So when you take Y over here, you get SI, XI, Y inverse is in R. And so the product just takes care of every possibility here. So what does this mean? This conducts each one of these generators into R. So SY inverse is in I inverse. And so what do we get from this? Well, SY inverse is in I inverse. So SY inverse Y is equal S. And S, so this is an element of I inverse. Which is contained in M. Right? Does this. Therefore, S is in M. And it's in R minus M, which is a contradiction. Hence, I inverse is contained in no matter what. So I inverse. And that's the other direction. Okay. Any questions on this? Yes.
In parentheses, you have xi equals r times y divided by something.
Okay, so what do I have here?
In the parentheses, what's the
Oh.
denominator?
Oh, this is not the same as down here. It's some. This is actually, these are actually both elements that I can divide by. So it's something in, not in M.
Okay.
Right, so it's just anything that's in R but not in M, right, that multiplicative set. Okay, okay, any questions? Let me point out, before I move on, we're gonna come to this later, but the hypothesis um, hypothesis that I find generated necessary in this direction. So that is to say, one can find an ideal not finitely generated such that I am this principle of M in Max regard. Here's my challenge. Maybe I'll add this in the next homework. Anybody give me an example? An ideal that is not finitely generated. But when you localize that ideal, every maximal ideal is principle.
You want me to say maybe a guess or,
Was it?
well, if you're gonna put it on the homework, I don't wanna like say it's something.
Oh, no, I'll like, I'll have a little party in my head here if you give me an example.
Well, I mean, I don't know if it's right, but if you take like a polynomial ring and like infinitely many variables, then the ideal generated by each of like all of the
Variables.
variables.
Right, but the problem here is. So what's your ideal there? That would be not finitely generated, but locally principal. At every, would it be that ideal generated by all the variables?
Yeah, and then it would be,
The problem is, that's a good idea.
I guess you have the. You have some maximal ideals that don't look like,
if you take just the ideal generated by the variables, you localize there. The problem is now this ideal up here, it's not principal. Right, it's not locally principal at that particular maximal ideal.
right,
Does it have something to do with the group part of the ideal?
What's in there?
Does that have something to do with like the group part of the ideal? Because I know if a group that's,
Oh, so what's the property of the group?
yeah,
A group, oh, what is it like locally? Yeah, it's more complicated, I think, right? So let me show you how you might build it. Start with. I'm gonna have a seed ring and I'm gonna build something. So let's start with. Really, the only thing that matters here is this is a principal ideal domain. With one non-zero prime. In this case, it's X. So basically, this ring is very, very easy to understand from a certain point of view, because everything in here is either zero or it's a power of X times n, and that power of X could be zero, it could be in it itself, right? And here's what I'm gonna do. And I might ask you to fill in some details on this. I'm gonna have to think about how to set you up for this, but. We'll call this ring R0. This is our seed ring, so to speak. And there's one prime, and we're going to call it X. There exists a quadratic extension of this, where X splits into P1 and Q1. So what you can do is you can basically come up with an irreducible polynomial that involves X. Or, well, in fact, what you could do, and a naive thing to do it, is you can take the ring and adjoin the square root of X, right? And then, but I want to vary the polynomial. I don't want it to be a perfect square. I want it to split into two separate. Remember how in our quadratic rings of integers example that we had earlier, when you start with a prime in the integers, there were basically three things that could happen. The prime either remain prime, right? Or it's split into two different primes. These could be prime ideals, but if it was a PID, it's split into two primes. Or it could be the square of a single prime, right? I want case two. I want this to split two different primes. So I could do something like take the root of the polynomial y squared plus y minus x, or something like this, that makes sure that you get two separate solutions to this. And actually, just to make this easier, let's make this a finite field. So you split this into two primes, all right? Now, with some stuff we're going to do later with the integral, you can argue that in fact these are the only two primes in here. And so these prime ideals both have to be principal because it's because they're only finite many primes. What you do is you now build a new quadratic extension of this, where this one remains prime and this one splits. So the fact that you can do this is kind of a famous theorem. You can find it in Gilmer's book. We haven't done this yet, but you can do this where you can pick the polynomial sagaciously such that this remains prime and this other one splits into two different ones like this. Now you go to the third quadratic extension, where these two primes remain prime and this splits. Notice that at any stage of construction, there's only finitely many primes, right? So for example, in R0, there's only prime X, and R1, there's these two primes, and R2, there's 1, 2, 3 primes, and R3, there's 1, 2, 3, 4 primes, and so forth. And what we do at every stage is we leave n minus 1 of the primes alone and we split the last. We continue this process forever. And there's our stairway to heaven, so to speak. Okay. Now, in this, we'll let R equal the union of all the RIs. Max spec R. So the maximal ideals, it turns out that this ring is also one-dimensional in the following sense. Every non-zero prime ideal is maximal. Let me list the primes. P1, P2, P3, forever. And the notorious VIG prime. And I'm here to tell you, this is big because in fact, I can generate it. It's not finite.
So I was thinking of like something like people's community, something along those lines, but maybe I'm too far in my head with that.
Well, yeah, if you did something like Peter's community, they'd have to go on forever. But this maximal ideal is generated, and notice at every stage, these generators become redundant, right? Because notice that Q1 is generated by Q2, right? Because P2, Q2 is Q1, and Q2 is generated by Q3 because P3, Q3 is Q2 and so forth. And so once you have Q2, you can throw out Q1, but you go on forever, so you can't, right? Yeah, right. But this maximal ideal is generated by all the Qs, right? And that's it. There are countably many maximal ideals. Right? The big one is not finitely generated. And here's my argument. If the big one M was finitely generated, it would have to be generated by some maximal Qi. But it can't be generated by Q1 because Q1 doesn't divide Q2, right? Q2 is in fact a factor of it. It can't be generated by Q2 because of the Q3 and so forth and so on. So this ideal cannot be finitely generated. Okay, so now let's look at that maximal ideal. Right. Let me point out that if you look at R localized PI and N's PIs, then M PI is local principal, is principal. Because in fact, it's equal to it's generated by 1. You might explain why this is true. Well, what are the denominators allowed let's just, for ease, let's just take P two, right? What are the denominators allowed in R localized P two? It's everything that's not divisible by P two. Right? Now Q one is divisible by P two, Q two is not. So in this ring here, Q two is allowed to be a denominator, right? And in fact, in general, in R localized PI, QI plus one is allowed to be a denominator. That means the multiplicative set hits the ideal, so it blows up to the entire ring. Right, so what that means, since in any of these things here, you're allowed a denominator of some QI, that means, and since all the QIs are in here, that means the maximum ideal blows up to the whole ring because it hits the set of denominators. Right, so this is locally principal at almost every ideal. What about the big one? What about M localized at M?
Is it the other way around?
Anybody, actually, this was principal. Right? M itself is not principal because we had this problem right here, right? But M localized at M is principal. Anybody see what the generator is? Just guess something. You've got a 50% chance.
It's any one of the QIs because they're
That's right.
multiples of each other.
I'll be even more dramatic. Generated by X. Right? Why is that? Why is that? Well, here's the reason. Notice that X, for example, is equal to P1, Q1. Right? That's the way we built the string in the first place. Right? But in RM, P1, I'm sorry, not, yes, P1 is a unit. So X is the ideal generated by X is the ideal generated by P1. Right, because they vary by a unit, right?
Generated by Q1.
Oh, I'm sorry. Yeah, I think it's Q1. Right. Also note, Q1 is equal to P2, Q2. But P2 is a unit. So, this means that the ideal generated by Q1 is the ideal generated by Q2, which we already know is the ideal generated by X. And so, in other words, X locally, when you turn everything outside of this maximum ideal that goes up the right chain, when you turn all that stuff into units, it all collapses all these generators that I needed for M globally into a single generator. I call it X locally. And so M localized at M is also locally principal. Because at when you localize at every maximal ideal, it's principal ideal. It's usually the whole ring, and in the one exceptional case, it's generated by that bottom element X, and that's good enough. Right? So this is a good example of an ideal that cannot be finitely generated globally. But when you look at it locally, it's always principal. And why that hypothesis is actually needed in the first direction of theory. Okay, any questions on it? Yes.
What exactly do you mean when you say something locally?
That means that we say, so I'll make that precise. I in R is locally principal if, in the sense that we're using it here, I localize M and R localized at M is principal for all M in max spec And that's exactly what happens to M here. When you localize it, these maximal ideals is generated by one. When it's localized at its own ideal itself, it generated by X. Okay. Question. I think this is a really neat example. Yes.
So, do you think I and ideal of R has to be contained in R, if you're calling it locally principal, but what you have up there is not contained in R?
What's that? What if it's not contained in R?
Well, in your definition of locally principal, you have that I is contained in R, right? But over here, you call something locally principal that's not contained in R. Am I misunderstanding something?
Yeah. That's right. M and R is local principal.
Okay.
Right, this is what helped get that conclusion. There you go.
Yes.
And of course, I should point out, I guess, that any principal ideal is locally principal.
So in that top line, where we localize a PI, why is it that that is getting it seems like that would. It seems like there are things in M that aren't units. Wouldn't that be generated by QI minus one?
Oh, you know what? So that makes M blow up. So M localized this.
Because those are all the Qs below that P are still in that ideal P, right?
And local, so, yeah, so this should be in, that's right, so what am I thinking here? No, you're right, Grant's right about this, so, let me correct that. Yeah, I wasn't thinking straight. So if you look at M localized at, it's in PI. Right here. Then everything outside of this PI is turned into a unit, right? So that would be QI plus one and further, right? Because these are outside this. But everything inside this, so all the Qs lower are still good to go, right? So when I localize at M, when I localize PI, when I look at M localized PI, the stuff up here becomes units, but this stuff down here does not. So this should be generated. This should be.
No, you were right. Because M contains units.
Right. Yeah, that's right. So on the surface of it, what happens is these seem to survive, but what happens is M itself, that contains a unit.
Yeah, okay.
M contains this, right? So let me clarify this. Something right down here. So notice that in localized PI, we have localized PI, which is, I guess we have 1 over QI. Right. Therefore, QI equals 1, which is in M PI. Therefore, MPI is RPI. There we go. Yeah, that's right. The multiplicative set hits the ideal. I should have stuck to my guns on that one. Oops. Okay. So, yeah, so this is kind of an interesting example, and this is actually something that we're going to see. I'm fixing to find something called a Dedekind domain. This is something called an almost Dedekind domain, because what happens here is if you take this ring here that I've built and you localize it any maximal ideal, you actually get a Noetherian valuation domain. So if you localize it any of the maximal ideals, you get a principal ideal domain that has only one non-zero prime. Okay. So we've spent some time talking about valuation domains. This is kind of another. How many of you have heard of Dedekind domains? How many characterizations of Dedekind domains do you know?
A billion.
Yeah, there's something like a Google of these equivalent. Dedekind domains are very important. How many of you have ever heard of a Prufer domain? That's a little less. A Prufer domain is sort of the more natural extension. These are both globalizations of valuation domains. I should call this section Prufer domains because they're the obvious analog, they're the global analog of valuation domains. But Dedekind domains are important because they're the nicest of the Prufer domains. Those of you that are fans of algebraic number theory, when you're looking at rings of algebraic integers for any of their incarnations, then what you're looking at is Dedekind domains. And in fact, they're Dedekind domains that are even nicer than your Garden variety. So, definition. I'm going to start this way, and then I'm going to give you. This is going to be my basic definition. A domain R is a Prufer domain if every finitely generated ideal is invertible. And just so I can get more around this here, let me tell you what a Dedekind domain is. Dedekind domains actually have a lot better properties than Prufer domains in general. So a Prufer domain is a domain where every finitely generated ideal is invertible. Here's the way I like to think of it. All invertible ideals are finitely generated. So what a Prufer domain is, everything that can be invertible is invertible, right? A Noetherian Prufer domain is called a Dedekind domain. So what must be true of Dedekind domains then?
Every ideal.
That is correct. If R is Dedekind, then all ideals, then it's Noetherian, so all ideals are finitely generated. All non-zero ideals are invertible. So Dedekind domains or integral domains for every ideal that is not zero is in fact invertible. And if you've got an honest to goodness Prufer domain that's not Dedekind, then it must have an ideal that's not finitely generated, hence it must have something that's not invertible. example. Any ring of algebraic integers is Dedekind. Any PID is Dedekind. How about an example of a Prufer domain? Look at some fun examples. Prufer domain, D bar, a set of Z and complex numbers such that P of Z is 0. Some monic polynomial P of X and ZX is Prufer. The ring of entire functions on complex numbers is Prufer. I feel like a total jerk for doing it this way. The example we just did is Prufer. But in fact, in a certain sense, these ideas are all too good. In fact, these are all basic. Which is, in a certain sense, better than Prufer. Any Bayesian domain is Prufer. Let me make this observation. Why is that?
It's finitely generated ideal is principal in the Bayesian domain, and the principal ideal is invertible.
If R is Bayesian, every finitely generated ideal. Yes. How about some examples of Prufer domains where they're not basic? So there are some finitely generated ideals that aren't principal. Oh, here's one. This is almost cheat. This is a Dedekind domain, and it's got ideals that are not invertible, or that are invertible but not principal. Namely, the ideal 3 generated by 3 and 1 plus right.
What about one that's not notarian and not Bayesian?
This one is neither Bayesian nor is
Oh, I'm sorry, I didn't finish.
So take power series over this field with constant terms which we here. This was almost cheap. Here's another one. The ring of integer value polynomials is another good example of proof of domain that is not basic in general.
Ring of integers is Z or as in algebraic integers?
What's that?
Ring of integers is in Z or ring of integers is in rings of algebraic?
Well, you could do integer value polynomials for like lots of different domains, right? But yeah, I'll remind you, I'll just think about that next time. Anyway, that's enough for today. Any questions? Any questions? Adam, any questions? Okay, good to go. All right, well, I will see you folks next time. Yeah, rings of algebraic integers.